Hey y'all, welcome back to another round of engineering. And yeah, let's get going. So previously we've been dealing with RC circuits or RL circuits, and the topic that we still need to cover are what happens when we have all three, these so-called RLC circuits. Okay. Now, in the discussion about the RLC circuits, we run across a new idea, namely that we have second order differential equations. You know that if you have an RC circuit, for example, you have dq dt's, otherwise known as the currents, and q's. And this gave us the first order equations, and we would find solutions on the order of e to the negative, say, t over rc, some variant of that. And similarly, when you have RL circuits, you have di dt's, the changing currents, and the i's. And again, you'll run into something like this, where you have some resistance divided by the inductance. But now with these RLC circuits, we are going to have, I'll express it in terms of Q's, we'll have second order derivatives, first order derivatives, and the originals. And the question then becomes, how do we deal with solving those equations? Okay. So that's kind of the broad topic. How do I actually solve these things? Now, unfortunately, as I was going through and thinking about it a little bit more, I realized that in order to solve these things, they are also intimately tied with some mathematical concepts. So for better or for worse, I decided I'm going to cover some of these mathematical concepts first with the point of view of finally solving these second order differential equations at the end of the day. Now, not to worry, these mathematical concepts come up again in other parts of the class. So it's not time wasted, but it's just, this is probably the most opportune time to present them. Now, that's the end goal. Now, along with that, we're going to actually have to present several different concepts. And so the thing that I'm going to start off with is Taylor expansion. Taylor expansion. And so we'll start off with that. And in particular, I'm going to be interested in the Taylor expansion of three different functions. Okay, so I'll put in parentheses here. We're going to be interested in three different functions, sine of x, and cosine of x. So e to the x, sine of x, and cosine of x. These are the three functions that we will be interested in with the Taylor expansion. So that's step one. The second step is going to be introducing an idea called the complex number. Now, sometimes you will see this expressed as I. You'll sometimes, in a physics book, for example, you'll probably see it as an I. Engineering textbooks tend to use the letter J instead, because you don't want to mix this up with the time-dependent current. So our book and most electrical engineering textbooks will use J, and I'll try to make it kind of this more stylized thing, cursive J, if you will. So don't use I, okay, use J. And we are going to have a discussion about what J does. And why is it important in this context? We will be able then, coupled with the Taylor expansion and the complex number, we will then move into what's called Euler's relation. Euler's relation. And we can derive it, but at the end of the day, we'll find out that there's a very interesting phenomenon that occurs when you take the natural number e and raise it to an imaginary power. I know that seems weird, doesn't it? Okay, so when we take e and raise it to the imaginary number, we end up with a very interesting relationship that we're going to take advantage of. And then lastly, Once we have these three mathematical concepts under our belt, then we'll be ready to talk about second order differential equations, diff EQ, with constant coefficients. Okay. And that this e to the j theta will actually help us explain some of the solutions. Okay. So that's kind of the long-term process. And depending on how long this video takes, we might have to break it up into two just to kind of give ourselves a breather. Certainly there'll be a break here. It's just a matter of how far along we go. Okay, so that's kind of the order of things. Now, the last thing I will point out is that this Euler relationship will come back. Okay, and in fact, we'll be using this complex number and the Euler relationship for what we call AC circuitry, alternating current. Okay. This two ideas will make it very easy for us to treat more complicated circuits. So stay tuned. Okay, so let's get at it. I said, oh yeah, the first thing is a Taylor expansion. So you should have seen Taylor expansions in a math course. Now, whether that be Calc 2 or Phys 245, you will see this at some point if you haven't already. Okay. And the basic idea of a Taylor expansion is, okay, so number one, you have to have a nice function. Have a nice function. What does this mean? A nice function is something that I'll call it infinitely differentiable. Okay. Or maybe I should say infinitely differentiable. And can I say integratable? Probably integratable as well. Okay. In other words, there are no cusps, there's no discontinuities, etc., etc. Okay. And you can see, for example, how functions like e to the x, sine of x, cosine of x, ln of x, these all end up being these nice functions where you can differentiate them infinite number of times. Okay, so I've convinced myself the integratable part is not necessary. Let's say infinitely differentiable. Okay. That's the starting point. So if you don't have a function that's infinitely differentiable, then these Taylor expansions are not going to be particularly useful. Okay. Now we could go at this a couple of different ways. I'll give you two examples, and hopefully that'll be enough to kind of convince you about what the problem is or how to do this. So the first case I'm going to go as a heuristic argument. And this will get you part of the way to understanding what Taylor expansions do. It'll be off a little bit in terms of coefficients. Okay. So imagine for a moment that you have some function. So you have your y values, you have your x values, x, and you have some function. And it doesn't really say it's nice and smooth, so it's nice and infinitely differentiable, smoothness. Okay. Now the question becomes, if I have a value of x, so you know you have a value of x, and you know that, let me call this x naught, and you know that the function has a value of f of x naught. Okay. Now the question becomes, can you approximate the value of the function, I'll say f of x naught plus some delta x? In other words, is there a good way to get an idea about the value of the function if I am in, and this is the term that mathematicians use, if I am in the neighborhood of x naught? Okay. So the neighborhood of x naught being some distance delta x away, how does that affect the values of my function? Can I get some approximation for that? Okay. Now, I'm sure you're probably aware, okay, if I want to guesstimate the value of the function given a small variation in the value of x, one way to do that is that I see the slope of the function. If I take the slope of the function, okay, so f prime, if I take the slope of the function at x naught, that gives me an idea about how quickly the function is changing. And so if I want an estimate of the function value at a distance of delta x, I could approximate that as the value of my function evaluated at x naught, and then add to that the derivative of my function evaluated at x naught. So this is giving me the slope of the function at x naught. And then I multiply that by my step size. Now take that in for a second. Convince yourself that this is okay. You got it? Okay. Yeah. So if you have the slope, here's your slope, here's your step size. This gives you how much, I'll say delta f, how much the function changes in x naught around that point. Okay. And then you have to add to that the original value. So you have the change plus the original value gives you your final. Good so far? Okay, so the next thing, okay, well, that's okay. That's all fine and dandy if the function doesn't change very much, if it's a slowly changing function. But what happens if I zoom in? So let's get rid of this. If I zoom in, perhaps maybe the function changes really rapidly. Still smooth, but it changes really rapidly. In other words, I need to get an approximation. This tells me how much the function itself changes, but I might need to know how quickly the derivative changes around the position x naught. Right? So I need to know not only what the value of the derivative is, but how quickly the derivative is changing. Get an approximation for that. Well, hopefully you see we can play the same song and dance. This would just simply be the derivative evaluated at x naught plus, I'll put in here the second derivative evaluated at x naught times my step size. Okay. And you see that now we can take that, okay, and we're going to end up plugging it in for that derivative there. And so what do we have now? We have that the value of the function in the neighborhood of x naught is roughly equal to, I'll use the approximate, f of x naught plus f prime of x naught times delta x. And then we could say plus f double prime of x naught times this guy squared. And then keep going. Keep playing that song and dance. Well, what happens if we want a better approximation for f double prime? Well, that will relate to f triple prime, etc., etc. Okay? That is the basic idea of the Taylor expansion. Okay? It is trying to find an expression for the function in the neighborhood of x naught, expressed in terms of the value of the function at exactly x naught. Okay. Let me say that again. It is trying to find an expression for the function in the neighborhood of x naught, that's what that delta x represents, based solely on the values of the function and its accompanying derivatives at exactly x naught. Seems kind of cool, actually, right? I can say I can say what the value of the function is right here, I mean, right over there, based on the value of the function right here. And I say the value of the function and its accompanying derivatives. Of course, again, this highlights the fact it has to be a nice function. The fact that it's nice, smooth, infinitely differentiable means that the information that I know about the function here allows me to project what the function is over there. Okay. It's kind of cool, actually. So that's what the general Taylor expansion is. Now, this gives you kind of a heuristic argument for how the Taylor expansion actually works. Okay. Now, it turns out there's some coefficients in here that I'm not particularly good about remembering, but let me give you the full-blown expression. This is just an approximation here. Okay. So the full-blown expression, if you want to do a Taylor expansion, okay, and keep in mind, this is the value of a function at some nearby point. So sometimes you'll see it written as x naught plus x naught plus delta x. Sometimes you'll just see it written as f of x. Okay, so it just depends. So what would this be equal to? This is equal to, as you've already seen, the value of the function at the original location. Okay, so nothing fancy there. Plus the derivative of the function at the location x naught, okay, times delta x. Okay, so I will put x minus x naught. So I'm writing that out explicitly. Then you go plus, and I'm gonna, to make this more explicit, I'm gonna put it to the first power divided by 1 factorial. I guess I could have done this first one as x minus x naught to the 0th power. To the 0th power. Oops, I said 0th and then I wrote a 2. So I guess we could write it like this, just to make the pattern more explicit. The next one is going to be f double prime evaluated at x naught, x minus x naught squared over, yeah, you got it, 2 factorial. Okay. Plus dot, dot, dot. So that is what we call the Taylor expansion. Again, remember, you need to have nice functions. And that, again, should come into play based on our heuristic argument, and also seeing that, you know, you can't have these derivatives blow up to infinity. Okay. Or some sort of discontinuity, some sort of cusp. Okay, those are no-goes. Cool, huh? Now, here's the other thing. Okay, you'll sometimes see it generically referred to as a Taylor expansion. I have no idea why, but if you happen to be doing this at the origin, in other words, setting f or x naught equal to 0. You're interested at the behavior in the neighborhood of the origin. Generally, this is referred to as a Maclaurin series. I have no idea why Maclaurin got that named after him. None whatsoever. Okay. Maclaurin series is just a special case of a Taylor expansion. So there we go. The last thing I'll mention, and then we'll get some practice about doing these Taylor series expansions. You say, I mentioned this is in the neighborhood of x naught. And I'll put that in quotes. So the issue is the further away from x naught you want to evaluate this function, the more terms you will have to include in your Taylor series expansion. If you want to get a good approximation, the further away you get from x naught, the more terms you'll have to keep in the expansion in order to have a more accurate approximation. Okay? Now you'll find this handy. I mean, in this course, we'll use it for showing Euler's relation. But in other courses, okay, it sometimes comes into play that you get, say, a function that you just can't integrate by hand. Okay? Something that's just terribly difficult to integrate by hand. But you might have something that it's terrible to integrate by hand, but you could do a Taylor expansion and get an approximate function value and then integrate that. In fact, that's usually what happens. If you ever take Phys 225, modern physics, for example, that's something that happens. We get this terrible integral and we do a Taylor series expansion and then get something that we can actually integrate by hand. Okay, good. The second thing I'll point out to you, that's the neighborhood of x. Okay? The second thing I'll point out to you is look at the Taylor series expansion, and you notice that we are able to turn our function f of x, we are able to turn whatever function we're dealing with, f of x, into a linear combination, it's not linear, a combination of polynomials, not linear. Right, look at this. We have taken our function f of x, and so long as it is a nice function, we can express it as the sum of polynomials. And I'll write this out. We'll put f to the n of x naught over n factorial, n equals 0 to infinity. And there's our polynomials right here, which is kind of cool. Some people, I think this is sometimes referred to as a power series expansion. Right? You are expressing a function as a summation of powers of x, which is really cool. Also very helpful in the future. Okay, so let's get some practice. Okay. Go ahead, take a minute and find an expression for e to the x. So go ahead, take a minute, see if you can come up with the Taylor series expansion for the function e to the x. I'll just call it f of x. In fact, yeah, why don't we do this? Say f of x and let's call x naught equal to 0. Okay. Go. You got it? Good, 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 good. Okay, well, let's go ahead and walk through. Okay. So first of all, we need to take derivatives of the function. So I like to think of it as f of x naught, and that one we're already set with, e to the 0, so this is 1. Well, we also need to take the derivative of the function evaluated at x naught, and be particularly careful about the order. Okay? You need to differentiate, then evaluate, then evaluate. Okay? If you evaluate and then differentiate, you get 0, right? So it's differentiate, then evaluate. Sometimes instead of writing f prime of x naught, some people, myself included usually, I will sometimes write it as f prime of x to remind myself I'm taking the derivative first, evaluated at x naught. So you might see this notation as well, that long bar meaning evaluate. Well, this is nice. The derivative of e to the x is e to the x. So I get e to the x evaluated at 0, and so I get 1 again. And the second derivative, so I'll switch back to my other notation, is also 0. Or excuse me, e to the 0, and I get 1. Cool, huh? So what's our final expression for e to the x? Well, e to the x can be written as our original function evaluated at x naught. Okay. Then we have the derivative of our function evaluated at x naught times x, and I'll put in the x naught explicitly here just to remind us, to the first power all over 1 factorial. And I keep going. Well, the second derivative is also 1 times x minus 0 squared over 2 factorial. And I keep going, dot, dot, dot. Well, we could get rid of all these zeros. And usually when you do a Taylor series expansion, I would say most of the time, you end up seeing a pattern. And if you can get the pattern, then you're good. So e to the x, you can see the pattern. Again, it is just simply x to the nth power divided by n factorial. And we can do this from n equals 0 to infinity. Which means I can, now my neighborhood around 0, I can choose to make it as large as I want. Right? I could say, well, I want to know what the value is at x equals 10. What that means is that I simply have to take this and I have to keep a lot more terms. Pretty cool, huh? Yeah, let's take a look. And I'm not lying to you here. Let's queue up Desmos and just take a look-see. Okay. There we go. Graphing calculator. So let's go at it. So we have e to the x, just to give you an idea. Okay. And so now, blows up. So let's go ahead and take a look at our various functions. So the first term is just 1. Oh, it doesn't even plot that. Let's try this. 0 times x plus 1. We'll trick it into thinking about a function. There we go. So not very informative. It gets the x equals 0 part right, but then everything else, it's terrible. So let's go ahead and add in a second term. So now what we have is our first term was 1, then we have plus x. And now you see that the neighborhood may be, let's say, within x equals 0.25. So plus or minus 0.25, you see it does okay. But then outside of that range, it's terrible. It starts to diverge dramatically. Okay. So let's go ahead and add in our third term, x squared over, oops, excuse me, x squared over 2. And now you see that we're good almost to, let's say, plus or minus 0.5. Well, let's keep going. Plus, okay, so now you see the pattern. We have x to the third divided by, now we have to be careful, it's 3 factorial. So that's 6. And now, all of a sudden, hey, that doesn't look too bad. Right now, we might actually be able, depending on what your tolerances are, you might be able to get up to, oh, excuse me, these hash marks are half. I thought they were 0.25. You might even be able to get up to 0.75 now without having some wide divergence between the two. And we keep going. So depending on how precise you need to be, 4 factorial is 24. All right, you see it's even doing well on the bottom side as well. Pretty cool. And you can keep going, right? For however long you want. So 5 factorial is what, 120? Not bad, eh? Look at that. So that's just one example there. Okay? I don't suppose, oh my goodness, holy cow, are you kidding me? This is cool. X to the n divided by n factorial. Oh, that's so awesome. Look at that. Right now, oh, that's so cool. Right now, I've actually done it in terms of a function of a summation. So now I don't even have to type anything, right? All I have to do is change this upper limit here. Oh, that's so spiffy, right? 5, or how about if I want 7, 8, 9, 10. So you can kind of see, I wonder what happens if I just leave this as n. Oh, that's too bad. I was hoping it would let me do a parameter bar, like slide it. Maybe if I put a in here. Oh my goodness. Oh, that's so cool. Sorry, you guys don't know how lucky that you are. Okay, let's do this. This is, oh, I'm sorry, I'm geeking out now. Let's do 20, and I'll tell it to do step sizes of 1. Okay, so now we can play a video and we get to watch as it adds more and more terms. We get to see how much closer it gets to the actual value. Right, so you see as I add more and more terms, now I'm just subtracting them. You see how it does well going further and further out. So let's see if we focus in on the positive side for a second. Right, yeah. So it does really, really well. Oh, I'm geeking out here. That's cool. You guys are so lucky. The technology you have available now, like, that would have taken forever for me to do 15 or 20 years ago. Oh, that's awesome. Okay. There's enough of that. Play around with that. That's really cool. Okay. So we'll keep that up because I imagine we'll want to use it more. And we're done. Okay. And you notice that we can get the exact answer for any value of x. It's just a matter, again, of how many terms we want to keep. Okay. Second question. So geeking out time is done for a moment. Here's the next one. Go ahead. Give me the Taylor expansion for sine of x. And we'll say around the neighborhood of x equals 0. Go. You got it? Yeah, good. Okay, well, let's go ahead and go at it. Well, if I want to evaluate the function itself at x equals 0, I just get sine of 0, which is equal to nothing. That's kind of boring. But now here's the next one, f prime of x. Well, the derivative of sine is cosine, and evaluated at 0, and all of a sudden I end up with 1. And the double prime at 0, well, now I'm at negative sine of 0 equals 0. And I do one more derivative of negative sine gives me negative cosine, evaluated at 0, and gives me a negative 1. Hey? So what do we have? We get that sine of x is, I'll put approximate right now, and I'll go ahead and write all these in. I get f of f of x naught, so the value of the function evaluated at 0, well, that's 0. Then I get the value of the derivative evaluated, okay, so I get this over 1 factorial, right? That's this guy going in right there. Of course, you see now the next term is going to be 0. And the next term, so there's the negative from the -1. And I have, well, okay, yeah, I guess I could put positive and then put -1 in here. Okay. Now I have x minus 0. And this is the third derivative over 3 factorial. And if you keep going, you probably see that the next one's going to be 0. And the next one, what's the pattern? Go ahead, write down the pattern for me. Yeah, hopefully you see it. You get the next one is x to the 5th over 5 factorial. And the next one, negative x to the 7th over 7 factorial, etc., etc. So we can write this. There's a nice compact way to write this. First of all, can I somehow come up with an expression just to get the odd numbers? The answer is yes. So let's go ahead and we'll take the summation from n is equal to, we'll say 0 to as far as we want, an infinite amount. And what we can write is -1 to the nth power x minus x naught. Excuse me. We said x naught is 0, so we'll just leave it as x. And here's the secret sauce. Ready? I'm going to put 2n plus 1. And let's think about that. If n is equal to 0, so 2n plus 1, when n is equal to 0, I just get 1. When n is equal to 1, I get 3. When n is equal to 2, I get 5, etc., etc. So this 2n plus 1 allows me to increment n by 1, whole numbers, and it will produce just the odd numbers at the end of the day. So that's a helpful little thing to remember. That sometimes allows us to do some fancy summation notation. So in the denominator, I should have 2n plus 1 quantity factorial. You want to check it? Go ahead, check it on Desmos real fast. Yeah, let's go at it. Here we go. Okay. So I'm sure you've probably gotten it. Let's clear all these out. And what we want to do is plot sine of x. And now that I'm familiar with it, what we'll do is we'll do sum from n equals 0 to, I don't know, let's just pick a number. We'll say 10, just for kicks. Okay. And again, we have -1 to the n. Actually, yeah, -1 to the n times x, and now we have to be careful. Generous use of parentheses is always recommended, plus 1. Okay. And then lastly, we divide that whole rigmarole by 2 times n plus 1, excuse me, factorial. So cool. Oh, that's awesome. Here, let's try this. We'll put a in there and add a slider for a. We'll again set it from 0 to, let me go ahead and make it 20 here, because the issue is oh yeah, 20 is good. I was thinking it skips every other, but we've already taken care of that. So we see that when a is equal to 0, we just linear approximation of the sine wave. Now we have two terms, the linear term, x and x cubed. And you can notice that we're overshooting on the edges, which is why for the first one, say it's positive, then we subtract x to the third to take care of this overshooting on the edges. So we subtract x cubed, but now we're overshooting the other way. So we have to add x to the fifth, subtract x to the seventh, etc., etc. And so you see that as you add more and more terms, you're correcting further and further out. Here, let's make it, yeah, go. So you can see. In fact, let's make it 30, just for kicks. Go. So eventually, if you need to go further and further away, it's just a matter of how many terms you add in. Go. Do it for cosine. You got it? Yeah, good, good, good. I will leave you to figuring it out or writing out the whole thing, but I'll give you the final answer and we'll plot it just to make sure. So cosine of x, you'll notice when we did the sine of x, it contained only odd powers of x. Okay. Sometimes we refer, I mean, this should make some sense. Sine is an odd function. What that means is that if you take sine of negative x, that equals negative sine of x. And that relates intimately to this idea that you have just the odd powers. You'll notice that cosine is an even function. And that means that it just contains the even powers of x. So what we have here is we have n is equal to, I'll say 0 to infinity. We also have -1, and I'll put it -1 to the n. And then you'll see that rather than using the 2n plus 1, that gave me the odd powers of x, I'm just going to use 2n. X to the 2n over 2n factorial. And there we go. There is our Taylor series expansion for cosine. Okay, last one, I promise, but like I said, you have this powerful tool. When you have a hammer, everything looks like a nail. So let's go ahead. Let's do cosine of x. There we go. And instead of n plus 1, we just shift this so it's just n. So we have our cosine function. And go ahead. Go. It's like a bird flapping its wings. Fly away, little bird. Fly. Be free. Huh? Cool? Okay. Yeah. So I'll stop it there. Okay, good. So that's the first step. I know that's a little bit of a mathy video for today, but we'll start there. We've got an idea now about what is the Taylor series expansion and how can it be useful. Namely, you can take functions and approximate their values at different locations. Or on a deeper level, you can take functions and express them in terms of powers of x. Okay? So that's the first step we need. Next video, I think I'll talk about Euler's relation. We'll have to introduce this idea of the complex numbers and then how to use that to get this Euler relation. So I thank you for your attention. Keep up the hard work. I'll see you next time.